Hi, so my name is Etienne. I'm from Switzerland. I'm one of the Gradle Enterprise leads together with Luke. I've been with Gradle for close to 4 years, and I've been doing software development for about 20 years.
I'm Luke, all the way from Australia. I've been an engineer at Gradle for about 7 years now. I spent a lot of time working on Gradle itself in the early years, and for the last few years I've been working on the Gradle Enterprise project with Etienne. Today's webinar is all about how we approach having a fast and reliable CI process and pipeline, and we actually do it with the tools that we build ourselves.
So let me tell you just a little bit more about our development process, so you have a bit more context of why it is so important for us to have an optimized CI pipeline. On our team, we have close to 15 developers that all push to master. And we push a lot, and we push several times a day. And all of these changes are continuously deployed to one or more development environments. So it is important for a developer, once he pushes changes, to get quick feedback about whether that change was sound or not. So he can fix it if needed before he has moved or she has moved on to something else. It's also important for the other developers to know if changes that were pushed by somebody else were sound, so they know whether they can pull from master or push to master. So in short, quick feedback is really essential for us to stay in the flow and to make quick progress. And that quick feedback we can only achieve if we have a very fast and reliable CI environment. So what do we actually build? We are, not surprisingly, building Gradle Enterprise. Gradle Enterprise consists of various components that we're all building in an automated fashion. We have several apps that we build and deploy. We have documentation. We have supporting tools that we're building. And we also have the website. And all these components live in a monorepo. That monorepo has about 85 projects, about 2,500 files, and around 6,000 tests. A lot of these tests are integration and functional tests to make sure the components play well together. We also have, and we'll come back to that throughout the webinar, a lot of cross-version testing that we need to do because we have different Gradle versions to support against different plugin versions, the build-scan plugin version, and even different JDKs. So all this together gives us a matrix of more than 20,000 tests that we need to run for every commit to verify things are working properly across this matrix. And in general, we have a lot of automation in place. So all the deployments, changes, they are deployed automatically to different environments. Also, build environments themselves are set up in an automated fashion, and we also have the automated IDE set up. So Luke, why don't you give a bit of an overview of our general approach to CI?
Sure. So we have one key principle with how we approach CI and managing it is to keep it simple. Inside the Gradle build and our build logic, we have the definition of what depends on what and what needs what, and that's the right place for it. So how we manage CI and all that downstream, we try and keep as simple as possible and keep the complexity out of there. We have many small builds, so even though we have a single mono repo, we have many sort of CI plans or jobs, and they're all relatively small, and we build those in parallel. So we massively parallelize that, our CI pipeline. We have lots of build agents, so we have many machines, a farm of machines that can build this stuff, and that's essential for making it fast. We also heavily rely on the build cache. That's probably an understatement. This whole approach wouldn't work if we didn't use the build cache, and we'll come back and explain why that is and how that works for us. So that really makes us fast. And we use build scans all day, every day to help us debug when there's problems, fix things when we break things, and optimize this process and keep it fast. So that's generally how we approach it. What is a build cache? If you haven't come across this before in Gradle, so the general principle is it makes your builds faster by reusing outputs from previous builds. So if you don't have something like this, what you end up doing is building the same thing multiple times. So this avoids that by, if the same thing is already there, just reusing it. So we avoid a lot of redundant work, which frees up build time to build other useful things. And what's important about this, if you've been using Gradle for a while, this may sound familiar in the form of what we call incremental build, where Gradle will avoid something that you've just built. But the build cache really takes us a step further and reuses things from other machines as well. So we're going to build it once on one machine, then every other place that is needed, downstream in the CI pipeline, we reuse that way. So it's really, you can kind of think about it as an incremental build, but taken even further and more effective when you're distributing work across multiple machines. So what are build scans, if you haven't come across build scans yet? So build scans are a shareable record of what happened during a build. So that contains a lot of diagnostic information. If the build fails, a lot of information about why it failed, and all kinds of things to help reason about that. The performance profile is a significant part of it, and there's many aspects to build performance, and the build scan represents a lot of those and lets you really dig in and make things fast and keep things fast, which is critical, which we'll come back to. And there's much more as well. So build scans are created by there's a Gradle plugin which you add to your build, and then at the end of every build, this build scan is uploaded to a central server and stored. You can then access it later and share it. And we're going to be looking at build scans in depth and talking more about exactly how we use them. So we mentioned that we build Gradle Enterprise and work on Gradle Enterprise. Well, Gradle Enterprise is build cache and build scans. So while this is what we're effectively building, we're also using build cache and build scans in our own development process. One, for dog fooding reasons, so we can use it and get early feedback, but it's also just as a generic software team trying to build a product critical to our approach. It's very important there. So in Gradle Enterprise is server software that you install on premises. So if you're using Gradle Enterprise gives you build cache and build scans for your builds. Okay, so let's see it all in action. The first thing I want to mention is that for our CI tool, we use JetBrains TeamCity, and we really like it. We've been using it a long time. Generally, we're quite big fans of the products and tools that JetBrains make. We use a lot of them, and yeah, we like TeamCity. It works well for us. So here is effectively the root of our CI tree for the Gradle Enterprise project. As you can see, there are quite a few builds here. They're all relatively small. You can expand some of these out and see all the different sections here. So roughly each kind of project within the tree has its own build plan, and then even further as well than that. So what we're looking at here with these groups is that we break up test suites into multiple groups and split them up and run them across multiple machines in parallel to keep things fast. So that's one of the techniques we have. And Etienne mentioned that we do a lot of cross-version testing. With this particular product, we support many different Gradle versions, different versions of the build scan plugin over time, different operating systems, JDKs. So we have a big matrix of tests that we have to run, and there's just a lot of tests. Those are real functional tests that are quite slow, so breaking them up and distributing them is key, and also making them fast with the build cache is also key there. So this is kind of roughly what it looks like. We're going to talk a little bit more about how we deal with all these projects in a second, but so let me just go into this one here. So here's a particular build, and you can see here in the kind of status box in TeamCity, we're using a plugin for TeamCity that integrates with build scans that gives you that build scan link really prominently here. So if we run a build and we want to go and have a look at in depth at the results or debug it or something like that, we'll come in here and go straight to the build scan. So for all of our CI builds, we have these scans with all this really detailed information that we go and use to optimize and debug. And just one thing I want to point out is that we also have these build scans for our local builds as well. All of the builds that we're running day to day produce these scans. We can go and look at it with the same tooling, the same interface, the same approaches for debugging and optimization there. So with that many builds and things to configure potentially, Etienne's going to talk a bit about how we manage that aspect of it.
So as you've learned from Luke, we have two things that are key to us. We have a lot of builds, and they're very small, and we can run them in parallel, and we need them to be fast. Right, so let's look at these two things. Like you've seen here on TeamCity, we have a lot of builds, and it would be impossible for us to configure this all via UI. It's more than 120 builds, and if we also take our branches into account, we're ending up with more than 250, almost 300 builds. Right, so there's no way we could manage all these builds in a UI clickety-click fashion. So what TeamCity offers us is a DSL that allows us to programmatically configure and describe the builds that we want to run on TeamCity. Let me show you that in action. For that, let's take a look at some build scan builds. We have here some cross-version tests. It's actually 18 of them, 9 that run against Linux and 9 that run against Windows. And each of those builds runs a certain set of Gradle versions. Right? We have to support Gradle version from 2.0 all the way to 4.10. And so we group all these Gradle versions into 9 groups, and we then run those Gradle versions, those cross-version tests on 2 different operating systems. So how do we configure this? Using the Kotlin DSL approach that we have available in TeamCity. You can see an extract here. It is a bit closer here. Very easy. We're just iterating over the operating systems we want to support, Linux and Windows in this case. And then within each operating system, we create 9 builds. Each TeamCity build that we create, we then configure what we want to do, what do we want to run, what are the parameters to pass in. So with this little amount of code, you have code completion, etc. available as well. We can describe 18 builds, but we could as easily, of course, describe 25 builds if we wanted to split this up into more groups, or 26 groups if we wanted to have 13 for each operating system. It's a very concise way, a very maintainable way, and also a way that allows us to be very consistent in how we describe those builds.
This has been almost revolutionary for us using this approach. Apart from just the sheer power of being able to express so many builds concisely, having it be in code, we actually keep this in our same source repository as our code, having this defined. So when we make a change to the build to add a new module, change something dependencies, split up some more test groups, that same code review that is introducing those changes contains our CI configuration changes as well. So we review that as one thing, plus having all of the version control and all the rest of the tooling around this. So whatever CI tool you're using, check it if it has this kind of capability of being able to express its configuration in some kind of data or code format. And if your tool doesn't, move to one that does, because this is just so much better than having to configure things manually through a user interface and try and manage that. I cannot imagine going back.
Yep, definitely it's a big step forward for us. And then we apply common coding practices. So we extract things into multiple files, we extract things into different classes. And so ultimately it all lives in the .teamcity folder. It's part of the repo, like Luke said. And it's also checked in, and Gradle TeamCity picks that up as it configures the builds. So we have described a lot of builds, more than 120, like I said. But now we also need the agents that can actually run those builds. Otherwise, we have a bottleneck of running those builds that would potentially be parallelizable. The way we do this is we use Salt from SaltStack, which is an open source tool that allows us to provision agents in a very concise form. Again, you can describe the configuration, the deployment, and then we can easily spin up more agents. So right now I think we have a bit more than 100 agents live, but if we want to add more, because we have more builds to run at the same time, we can easily spin up more. So we both scale on how we describe the builds, but also on running those builds on agents.
Yeah, so I see this as another critical aspect of running builds at scale and fast builds. You just need to be able to scale horizontally with little effort. And deploying another 20 build agents isn't a big deal for us.
Yep.
And it's so much cheaper to add more machines than have the software developers waiting. It just makes great economic sense. So you really want to remove the bottleneck of having any manual work in creating and configuring those machines, so you can just add as many as you need to make it fast.
Yeah. And we have various scenarios where we wanted to upgrade the agents, new Postgres version, something like that, and doing that manually across 100 agents.
Yeah. We wouldn't do it, or it would take us a long time.
Yeah. And we would miss some agents, have inconsistent behavior. All right, so the second aspect, once we have a lot of agents that can run a lot of builds, is how do we make those builds fast? And there's a key concept to that I would like to explain here a little bit. So the way we've structured our CI, it's simple, but it starts with a seed build. And the purpose of that seed build is to run those Gradle tasks that we know are also called by downstream builds, by multiple downstream builds. And why is this beneficial? So when those seed builds run those tasks, they put their output into a cache, the Gradle build cache. And then the downstream builds that run the same tasks for the same commit, so it's the same sources to compile, for example, they can reuse what has been put into the cache by the seed build. So instead of all those downstream builds rebuilding the same things, recompiling, for example, the same things, they can just reuse what's in the cache. And so the only overhead that is left then is just extracting or getting it from the cache and extracting it on the local machine. But there's even a bit more that we can do. So the seed build not only pushes to the cache for downstream builds to consume, the seed build itself can reuse what it has put into the cache. So if you make another change, you push it, and the task you're running is not affected by those changes, and the previous build has already put the artifact into the cache, the seed build can as well reuse it. And the same is true for the downstream builds. If they run some tests, and the next time they're asked to run, that build is asked to run, if the test didn't change, the sources didn't change, the dependency didn't change, it can also reuse what has been put into the cache.
So just one point I want to make there that may not be clear is that we don't have any complex trigger rules or anything like that with our CI setup. So any commit that triggers the entire pipeline with all of those 20,000 tests, but any given change is unlikely to run all of those because we're using the build cache to avoid doing things like executing tests on a component that isn't changed. We run far fewer of those. So we don't have to reason about, okay, if we change this thing, then we have to run these tests or any of that. We just do everything and allow the build cache to avoid doing work that actually isn't necessary because that hasn't actually changed.
Yeah. And we used to do this differently in the beginning, and what I remember is we had all those trigger rules, and sometimes they were wrong, or they were right at some point, but they weren't over time, and so we wouldn't pick up changes, or we picked up changes that were not necessary. So again, it was not easy to maintain.
And they may be right at some point, but our code is always evolving. We're changing the structure,
Exactly.
adding new dependencies, and we couldn't keep those trigger rules up. So
Yes.
This is part of what I meant at the start. I said we just keep it simple at that level.
Yeah.
Just every change builds everything, but the build cache allows us to do that reasonably and not have every change take days to get through the CI pipeline.
Yeah. What we also stopped doing once we switched to this approach is we're not promoting artifacts anymore the way we used to. Like we used to build one artifact early on once and then just pass it on through the pipeline to avoid rebuilding it and making sure we're exactly testing against the same artifact. But now the cache has become our medium to promote the artifact, so to speak. But there are even more benefits to this approach. We've seen the whole CI. We can make the builds on CI very fast, but we can also benefit as a local developer. So if we have somebody in the USA or in Australia, doesn't matter.
It's probably try putting out that our team is actually geographically distributed. So we've got developers in Europe, in the US, in Australia, where I come from. You may have picked up from the accent. So what Etienne is about to go into here is really relates to that.
Yeah, that's true. Yes, so we're totally remotely set up. So if I'm building locally, or any developer is building locally, they can also benefit from consuming artifacts that have been put into the cache by that seed build. And we'll see that in action in a second. We're not actually pushing to the cache as local developers, because typically the changes you have made locally, nobody else will benefit from, because it's very unlikely that the other developers made exactly the same changes. Now, we can also have a whole network of build cache nodes, right, where they can replicate cache artifacts from one cache node to another. And that becomes very useful, I would say, especially for the poor people in Australia with low bandwidth and high latency, because we can now have can have a remote cache node in Australia in closer proximity to where Luke is living or other Australian people, rather than having to connect to a cache node that is, for example, in Germany, right, or in San Francisco. And that's offered by Gradle Enterprise, this cache replication. We can also have preemptive caching, meaning if the seed build pushes something to the cache, from that cache node, it's automatically published to all the other cache nodes. So overnight, while Luke might be sleeping, seed builds are running, cache artifacts are propagated all the way to his cache node in close proximity. And when you make your coffee in the morning, you run your build. Before you even have finished your coffee, the build's already ready
Yeah,
to go.
absolutely. So just to make this a bit more concrete, so we would build everything in the same mono repo, and one of the components is our entire user interface, which is JavaScript built with Webpack. And that takes anywhere from about 45 seconds to a minute to build. So a clean build of that. And I'm rarely changing that myself. But that is frequently changing. We have people in there making changes all the time. So every time somebody checks in a change to that, next time I go to build, potentially I have to wait that 60 seconds or so for that to build. But because with this approach, because by the time they've checked that in, the seed build has run, published it to the build cache. By the time I then pull the changes and go to build, that is in the cache and I get it straight away. So it's quite a big file. So if my poor internet connection at home takes about 2 or 3 seconds to download, but that's a significant saving. On 60 seconds, I'm paying 3 seconds. And this is happening multiple times a day. So that's the example of it. It makes a real difference. And with the replication, the latency and speed here is critical. So that's why having the different nodes in the different geographical areas is important. We're running many builds a day, even saving 200 milliseconds off a download or connection. If you're doing it that many times a day, it adds up to seconds. So speed is everything. So, and it's incredibly cheap. We just have some cheap AWS instances running with a cache node. You don't need big servers or anything like that to have as many of these as you need. So.
All right, let's see that in action from TeamCity. We have at the very top here the seed build. We call it build insanity check. That's the build that populates the cache for those tasks that we know are also being run downstream. We also have a second seed build, in this case, development build cache seed. And I guess you can derive from the name. That is a build that is focused on populating the cache with artifacts that we know local developers are also running those tasks, so they can consume and reuse those tasks.
We also have some optimizations in our build to make things slightly faster when doing local builds. So we sacrifice a small amount of accuracy to make things faster there, and that produces different cache artifacts as well. So we have, due to that situation, publishing, making sure that we are building those exact artifacts on CI and then seeding with that as well.
All right, and then we can look at some downstream build. For example, I'll take the server. So these are all going to be called downstream of the seed build. So let's take a look at one explicit one, which is the server component, which has been run here. And so let's see what happened in that build. And of course, I'm going to use the build scan to do this because it gives me a much richer model and much deeper insights of what happened. And if I just go to the timeline, I can see all the tasks that were running as part of that server build. And now let's see what was actually taken from the cache, because we expect this downstream build to be leveraging things that were put into the cache by the seed build. And we can see all these tasks here were using output taken from the cache, either because they put it in themselves, that build, or because the seed build put it in there. So let's take a look at a specific one. I'm going to just take this Webpack applet db compile Java was taken from the cache. If I open it up, see some more details, I can see it was very short to run, 25 milliseconds. And that's true for almost all these tasks in here that were taken from the cache. They take pretty much no time to run because they just have to get the artifact from the cache. But now let's take a look, how did it get there? So just via build scans, I can click here and I end up on the Gradle build that was actually producing that output and putting it into the cache. So we can see here we're again on the same task, naturally, because it's the same task that we're consuming from now. And we can see it took actually 9 seconds to run this task. And so if we run this task once in the seed build for 9 seconds, and then we have 5-10 builds that are consuming that, we're saving 10 times 9 seconds already on the total duration to get that change through the pipeline.
Can you just go back, Etienne, to the producer scan? So this is really a key point. One thing that people often question or wonder about when using the build cache, instead of doing something like promotion, is how do I know what's going on? Let's say I have some concern or question about a particular artifact or output, and then if it's being reused from cache, how do I get back to the root cause and trace that? Now, with build scans, because build scans understand when it reuses something from the cache, creating that link to, okay, this is the build scan for that build, I can now go and find out everything about that build that created that thing originally that I was reusing. So I can trace back to the source of that. So we've not had an issue on our project where we've actually needed this, but it's really good peace of mind. And if we did have a question about something, one of the artifacts that we are reusing, we have that information. The build scans, we can trace that back. So that's a key thing. Like I said, we haven't actually had to use it, but it's a necessary part of relying so much on the build cache that we can really understand what happened and where this was reused from. And of course, having so much information about the origin build is really important too. So for example, if you can go through to there and say, well, which machine did this run on? So if we just go to a separate section of the build scan infrastructure here, oh, it was on that CI agent, that machine had that operating system. So we have all really rich information about that origin there. So it's a key part of scans.
And to close the loop, we can then also see which TeamCity build ran that. So we have concept of custom links, which we're going to get back to a little bit later. We can also see that this was indeed a seed build that ran this task, put it in the cache, and then the downstream server build was able to consume from the cache. All right, so we know how to make things fast now, but now the challenge is how do we keep it fast?
Right, so as you already mentioned, our build and our project is always evolving. We're adding new functionality, new modules, things are changing, adding new tests. Getting it fast once doesn't mean it's fast forever. So keeping on top of things and understanding is key. So one of the tools that we use to do this is what we call a performance dashboard. So here's another part of the build scan application where I can see all of the builds that are happening, all the incoming scans. And what I want to do is have a look at all of the CI builds for .com project, which is Gradle Enterprise. We needed a name before we had actually sorted out the name, so that's why it's called .com. So I'm going to say, well, here are all my CI builds. So everything that is built on CI, we give it a certain tag, a build scan tag, and using this we can find all of those builds. Up here I can say I want to have a look at the performance of those things over time. So here's the performance dashboard for all of our CI builds. So just a bit about what we're seeing here. So this main graph here, so we've got a couple of things. So the white circle here is showing us the actual build time. The gray bar here is showing effectively the potential build time, but that's all time that we avoided or saved due to different avoidance measures, mostly the build cache. We'll come back and talk about that again in a second. And the green bar here is how much time we actually spent executing tasks in a serial manner. And you can't quite see it, but right at the tips here there are some little yellow bits, and that's indicating how much overhead the build cache is adding. So there are some pathological cases with the build cache. If you have a really bad network connection, the overhead can be non-negligible, and that's something you want to do something about. Or if you're producing artifacts with millions of files, the time spent to actually package those things up and send them around can be considerable. So this is something you want to keep an eye on and ensure it's low. And what we're seeing here is that there's quite a bit of variation. A couple of things I want to point out. This is the entire set of builds, and you can see it moving this little window here, and we have a sort of detail looking here. So let me go here, and if I look at one of these builds and I think, okay, that's interesting, something about that is something I want to know more about. I click on that particular entry, tells me what the build was, what tasks did it ran, I have the tags here, when it started, and a breakdown of the actual individual values for that build. I can, of course, then, if I want to find out more about that, go through to the actual build scan for that build. So for each of these metrics, so build time, how much time we spent executing tasks, we can actually dig in a little bit deeper. So if I'm just interested in, well, how long did things actually take? So I have a look at the build time here, and this has given me an idea of what's going on CI. So we can see by the general shape of this graph where many of the builds are very, very fast, right? And I know from looking at this data over a lot of time, that fastness is caused by being able to avoid the work by using the build cache. So if we look at it here, and I can see, okay, there are some spikes here. So we have a look at this section here. We're starting to get some builds up around 15 minutes, in this case, rather high. So I can see the shape of this, see anomalies, see spikes, and then go and potentially choose to do something with that. I'll come back to what we would then do to go and look at this and to make things faster, but I just want to dig a little bit more into the performance dashboard first. So I can break up build time into two different sections. So the whole configuration phase of the Gradle build and the task execution. So the configuration is something that runs at the start of every build and something you really want to optimize and get down. So I can isolate that aspect and look at it, and also just the task execution as well, separate that one. Within the task execution, I can break that down into different categories as well. So I can see how much time are we spending on tasks that aren't cacheable, how much are we spending on tasks that are cacheable but that we missed. There wasn't a pre-built version of that in the cache. How much time are we spending on cache hits, which is roughly how much time are tasks taking where we're able to reuse that from cache, and also just the things that are already up to date or non-actionable tasks in Gradle as a separate category. We can also break down the avoidance savings. So the avoidance savings are a measure of an estimate of time that we reduce the build by using different avoidance measures. So one of those is Gradle's incremental build functionality, which has been around a long time. And then we can look at how much time are we saving from the local build cache and the remote build cache. One other thing I want to point out is that these numbers here are mean numbers. So we're taking the average of the entire set. But to really get an understanding, you want to have a deeper look at those numbers. So if you hover over it here, we see a percentile breakdown. So I guess have a look at the P75 value here, that's telling me that 75% of builds are saving less than 7 minutes, but 25% of builds are saving more than 7 minutes of their total build time. So that's pretty considerable. And it's an interesting thing to look at the total time saved here. So we can say over this period we're looking at, which I know is about a week, we've saved 38 days of execution time via avoidance saving mechanisms, which, this is a week's worth of work. If it took us 38 days to build all that stuff, then we wouldn't be getting very far.
Look, I think it's worth mentioning, for those not so familiar, that even if we don't run a task, we know how long it took when it actually ran. So for up-to-dates as well as from cache.
Very good point.
By adding that up, we have the savings.
So we saw before that when we reuse something from the cache, we have the link to know which build it came from. So therefore, knowing that, we can say, well, how long did it take when that was originally built? And then the difference between how long that took originally and how long it took when it was reused is effectively what we've saved.
Yep.
So that's how that's measured. So, and we can see if we break that down, we're using the local build cache and the remote build cache for our CI builds. If you're using disposable builds and you don't have any kind of persistent disk across builds, you're going to be using just the remote cache. It's really kind of personal preference. We use a local build cache. It doesn't make a significant performance difference for us because the network connection between where we run the CI builds and the remote build cache is very fast. But being that we're people who also develop Gradle, reusing the local build cache on the CI builds just helps us kind of kick the tires on that a little bit. So it's not something you necessarily need to do if you have a reasonable connection between your CI build and your remote build cache. You can use just the remote build cache. So you'll see here we're saving an average of 2 minutes here, and if we look at the percentile distributions, that's how it works out. So a couple of things about our particular build. So if I was wanting to think about, can I make things faster with these builds? Actually, I'm just going to refine this search a little bit so we can look at a bit more homogeneous data, because this is all different types of our CI builds. They have different performance profiles. So let me just go and have a look at one of the components. Right, and this starts to look a bit more homogeneous now. Right? So this is the same thing being built over time as changes are coming through. So you can see that the total potential build time is about 10 minutes. The total height gives us an indication of that, and that we're really saving quite a bit via these avoidance mechanisms. This graph is mostly gray, which means it's dominated by the savings, which is great. So I said, okay, well, in the cases where we actually are executing things, what can we do here? What opportunities do we have? So especially when you're getting started with the build cache, and even over time as things change, what you really want to make sure is that you're not spending a lot of time on tasks that aren't potentially cacheable, right? Because then you have no chance of getting the benefits of the build cache. So this is something we keep an eye on. And in our particular case, we've all spent effort optimizing this build and made our expensive tasks cacheable and worked on that. But as I said, things change over time, regressions are introduced that changes situation. So by looking at these numbers regularly and keeping an eye on what's going on, we can keep it optimized and keep it working well. So of course we can spend time looking at how much time we're spending on build cache misses. If this number was particularly high, we could then go and dig in and look at this and say, well, can we break things up into smaller chunks that change less? And there's a bunch of things you can potentially do there as well. How much time are we spending on build cache hits? If this was really high, it's going to be an indication we have some kind of cache overhead problem, but this is really quite reasonable. And time on up-to-date and non-actionable to really just round that out. So one other thing I just want to point out is another thing that this graph gives us an indication of, the overall graph here, is how effective parallelization is for this build. And this number here also indicates that as well. So this metric of serial task execution, you can think about it as all of the tasks the build had to execute just flattened out, and how long would that have taken? So if you deparallelize it, how long would those tasks have taken? And this number here, 1.4x, is telling us that on average, if we weren't using parallel builds, the builds would be 1.4 times longer. We'll see why that's the case in a second. This graph is also giving us an indication that that number is not so big here, in the fact that these indicators here of total build time line up very well with the serial task execution time. So there's not a lot of parallelism going on. But this is a single component. So we wanted to have a bit more of a look at this. We can go through to the build scan, have a look at the timeline, start looking at the tasks that were executed and reasoning about why was it running in parallel or not. But let's just have a look at something that is more parallel. So if we look at the C build, which actually builds many more components, we see the situation is a little bit different. So here we have the build time marker being quite a lot less than the serial task execution time, which is indicating we're getting quite good parallelism. And we see here the mean number for this metric is 3.6x. So we're reducing, the build time is nearly a quarter of what it would be otherwise. And we can again see that on the timeline here, that we're getting reasonable parallelization here. Quite a comment, as I said, especially when starting out with the build cache, a key metric to pay attention to is this non-cacheable metric here. So how much time am I spending on non-cacheable tasks? If this number is high, that's a good indication that there's some fruit to be harvested there by going and making those things cacheable. But take an example build here. So a process I might go through with a build scan to try and work out what's happening there, or what to do next, how to optimize, is in the performance section of a build scan. I get many things, but we start with a high-level breakdown of the build time of this build. So overall, this took 4 minutes. I can see that the time to actually bootstrap Gradle here was rather high. And I know that in this case, we're probably spending quite a bit of time on compiling Kotlin scripts and some other things. And I can also reason about that. This was actually the first build of this project with the daemon. So we were building with a cold daemon here. So I know those numbers are about right for that particular scenario. This whole configuration profile section is really detailed information. I can dig into how long each build script or plugin took, which is a whole talk in itself. If I want to get that going then, but we're talking about optimizing for the build cache. We get into this task execution section here. We get a breakdown of the tasks that were executed during the build and what kind of category they had with regards to performance. So here I'm going to say that, okay, well, out of the tasks that we executed, in this case, we executed 111 tasks that weren't cacheable, and this was 24% of the task, and that took up to a minute, which is actually interesting. This is a build with a higher number for this than what we're used to. So if I want to see exactly what those tasks are and try and work out, okay, is there any juice in here in trying to make these things faster? If I click this link, it's going to take me back through to the task timeline, which we've seen a couple of times, with some filters applied. So it's saying, okay, show me all the tasks and that weren't cacheable. So I can see these highlighted in the representation here. They're in this list, and a typical process I would then follow would say, okay, show me out of those tasks the longest task that wasn't cacheable. And the build scan tells me here, okay, we have a task here that ran for 40 seconds, and it wasn't cacheable because of some overlapping inputs. Actually, this is interesting. This is a new problem that must have popped up quite recently. So I'm discovering this as I talk to you. So, which is good. So, if any of the rest of the team is watching, can someone log an issue to get this fixed, please? So, what I'm saying here is that we're spending 40 seconds on a task that may otherwise be cacheable, but because of a configuration reason, using the build cache requires tasks to be configured a certain way, and it takes some fine-tuning, and this is telling us there's a problem here. So there are some overlapping inputs. We've got two tasks writing to the same location, and it's also telling us which property of that task is problematic. So we can then go back at the build, look at that, separate these two tasks, and potentially save ourselves quite a lot of time, 40 seconds per one of these builds. Right, so there are many other aspects to performance optimizations with scans. That's some of the key ones. Like I said, you can dig into aspects of build cache, how that was used, the dependency downloads, how long those were taking, dependency resolution, whether you have some sections that are taking longer, etc. So that's a whole other session we could do on that just in itself.
Yes.
Having things fast is great and essential, but like everybody, I hope, we're not perfect and we make mistakes and we break things. So we also need to fix those as well. So Etienne, talk a little bit more about how we ensure that we fix things fast and fix them in a proper way.
Yep. Yeah, so in an ideal world, we would have an optimized CI just having fast builds. But reality is things go wrong, and they often go wrong in ways that we didn't expect, didn't anticipate. And then it really comes down to how fast can we identify the problem and fix the problem. Let's take a look at what do we need to really be fast at debugging and fixing those items. So what we need is more than just a log to figure out what went wrong in CI. We need a richer model, we need deeper insights so we can quickly reason about and understand what went wrong and draw the conclusions and fix. Also, when we have a CI issue that doesn't happen locally, which I guess everybody has experienced in their career, it can be quite a pain because then you have to log into the box, rerun the build, hope that you can reproduce it, maybe add some debug information, and if you're unlucky, you not even have access to the box. So we want to be able to still figure out what's going on or what happened if we cannot log into that box. Mm-hmm. We also want to add specific data about that build that will help us in case something goes wrong. Having that extra context about that specific build will help us once something goes wrong. And of course, the best help is oftentimes just asking a colleague, four eyes looking at it. So we need a way to easily share with somebody else what happened, what do we need, how can we fix it. So, and that's where build scans really shine as well, because they capture, like Luke said in the beginning, they capture what happened in the build, and we can use all that data to then reason about what went wrong and how to fix it. So let me give you a few concrete examples. I have picked out a few builds that went wrong, and just go through them and highlight different things. So you've already seen we can quickly go to the build scan from the CI build. So in our team, we really never use the CI tool, in that case, TeamCity, to investigate issues, right? The first thing we share is the build scan.
Yeah, it really handles the scheduling and execution for us, but the feedback and diagnostics we get from build scans.
Yeah, and I find it's a really good split as well. TeamCity does what it's best at, and build scans does what it is best at. So here we have a build. It failed. Something went wrong in the compilation of Groovy. We can easily see that. And sometimes the log does help us. In this case, it's not too bad to go to the log and find out what went wrong. But what's really nice here is we don't have to dig through the whole log, which might be 10,000 of lines of log. We can just go to that task and say, give me the log for explicitly that task. And that also works in the case of parallelism, where we have intertwining log output, which is pretty much impossible to then detangle just by looking at pure console output. We can get faster to the root of the problem and then start solving it, which of course in this case it's an easy fix, but it's also about easy understanding what went wrong. Here we have another build that failed, and typically we don't even check what went wrong here. We just go to the scan and get a richer view of what went wrong. We can see some functional tests failed for the plugin for 4.10 and also some tests for 4.9. Okay, so let's take a look at what went wrong with these tests, and we see a very rich view here to look into how many tests were run, how long did it take. We can also filter for certain tests, But in this case, what we are interested in is the failed tests. So we can easily see here what went wrong with those tests, because we can choose a single test and again see the output just for that particular test. And it's not part of the general log, but it's really the log for that test, where we can then understand what happened and fix it. So in this case, something didn't work with the dependency resolution. And now we have different ways to address this. One could be, or would be, we go to the dependencies and we start investigating how was the dependency pulled in. Let me just take one example, just taking any dependency here. How was Jackson pulled in? We can see that, who required it. So it itself didn't pull in any more dependencies, but others depended on it. We can also see from what repository was it pulled. And that can also help us when we want to debug dependency resolution issues. Right? So that's another example of how we can approach debugging an issue. Again, something went wrong. In this case, we see something went wrong with check style. So this is a code check tool that we have set up in our build with certain rules. And what's pretty visible here right away is that the report we get from the log, the first thing it's telling us, well, go to this other file. So now we have to go to this other file, which is not that easy on TeamCity, and figure out what went wrong. So what we want to have a faster way to identify the issue and fix it. So what we have here is we added a link that takes us directly to the check style report. So what happens here is we run the build on CI, we create that report, and we capture it as an artifact in TeamCity, and then we just link to that artifact. And the way we link to it is via a custom link. So that's something we add to every scan that is published.
So I'm just going to say, the Gradle build scan plugin that you apply to your build provides an API that anytime during the build you can say, here's a link to something, here's a tag, here's another custom value which you haven't tested. So it's a toolkit, and whatever makes sense for you, whatever kind of linking, you can easily add that to your build.
All right, so take a look. I click on that link, and now I see that check style report that was created, captured by TeamCity as an artifact, and I can now go to the one that had an error, and I can see what happened. Already a bit better than having to look at the log and then potentially even going to the box to find out what was written in that file. But we can do even better, and what I'm showing here for check style would work with any other code checking or even any other tool that you're running that captures some kind of metrics. And that is custom values. So like Luke said, in the plugin we can capture any kind of key value pairs, not just links, but also key value pairs and tags. And what we do is, whenever we run check style and something goes wrong, a warning, an error, we capture that as a custom value. So here we have only one issue. If we had multiple ones, we would all list them as individual key value pairs. And here we can see right away which file and what went wrong. So we're now at the fastest way to identify the problem. We saw check style failed, we go to custom values, and we can instantly see what went wrong.
So these check style issues are relatively common for us. We have fairly strict code formatting rules, and this tool enforces it. It happens quite a lot, and wanting to know what the actual problem is fast makes it obviously faster for us to fix it. So even with the report link, that we first did that was an improvement, but that report is still pretty noisy. I still have to work pretty hard to actually find the thing that I want. By putting that custom values, we know, okay, go to that. We've concisely represented it how we need it for us to be able to then go and action it. So one of those things was happening often, we're spending too much time resolving it. By using custom values and the extensibility of build scans, we're able to make it faster for us to resolve it.
And the mechanism we applied here, I think we applied for some other tool as well. And of course, whatever tool you use, like I said, as long as you get to the information of what went wrong, you can add it to custom values and then quickly surface that data. All right, and then the last example I want to show you, what can be very powerful is you run a build, it fails, so there is a strong inclination to say, well, let me check the last time it passed and compare what was different to last time I ran it when it was successful. Just like to briefly show that, I'm taking two builds here. We have one test that failed here, we're running some tests, and then the next build succeeded. So obviously something changed between those two builds, and in this case, we want to figure out what it was. So we can mark those builds and we can compare, and then we get a comparison of different data that we capture. So like infrastructure and the switches and different custom values, different dependencies, and also different task inputs. right? And armed with that information, we can then find out what was different between those two builds, and hopefully that gives us an indication of how to fix it. Mm-hmm. So these were just some samples that help us to really quickly identify when something went wrong on CI, why did it go wrong, and how can we then fix it? And so with that said, you want to wrap up what we...
So by using these tools and these approaches, what we get out of it is fast feedback. Right? That's the most important thing, that when I commit a change and I get it into master, where we're integrating all the time, if that has broken something or impacted something in a negative way, I find out about that fast, because of course the longer that takes, the longer that it takes to resolve. So if I find out about that in 5 minutes, I'm much more likely to fix it faster than if it's 30 minutes later when I've already moved on and context switched. So fast feedback, as we all know in software development, is absolutely critical. Another thing which we didn't touch on too much, but this has also been really transformative for us as well, is having a consistent debugging experience for CI builds and local builds. So what we see a lot is that people have their tools in front of them for local builds, and they sort of know how to deal with certain things there, and then it goes wrong on CI, and then they're lost. But by having build scans and having that same way of getting into the information and understanding and having work consistently in both environments makes us much faster and more effective at doing that. So I think that's a key point.
Maybe to that point, like personally, when I have a build that fails locally, I just click the scan and look at what went wrong. I don't even use the command line means that Gradle gives me to explore.
Yeah, I do the same. And actually, now realizing one thing we had touched on it, but didn't go into in depth, is that these build scan links are so shareable. So we're often in our Slack channel that we use, the development team passing these links around all the time to get help. Yep. And being able to do that for local builds and CI builds in the same way. It has the same benefits. With all the information and insight that the build scans give us, having a real sense of understanding of what's going on with build performance is also key. Instead of operating on sort of intuition and having conversations where we're guessing about how things are going and not basing those conversations on facts, that can just lead you to making wrong decisions. So we have a really good understanding of what the performance profile of our build and the CI in particular is like at any point in time, and feel confident that we're on top of it, or we understand the situation, and then make good prioritization decisions into optimization. The simple CI configuration, we talked a bit about this at the start, but this is something I really value, in that I don't have to think much about how our CI works. Just a change goes through, we build everything. I'm confident that works. The logic is very simple. I know that it adapts and evolves with us because it's so simple we don't have to change it. So I really value this approach. And also the thorough verification. As part of that, we test everything every commit, so I'm not concerned that we're missing things because we don't have those complex triggers set up right or anything like that. So I feel it's very well tested. And the faster local builds, as Etienne talked about when we were talking about how we arrange our use of the build cache, that's something, as somebody who runs a lot of local builds every day, I particularly appreciate saving all that time when I'm building stuff. So that's what it gives us, and at the end of the day, that allows us to develop better software and do it faster. So just a bit of a recap on the key points. Our whole approach to CI testing and delivery is predicated on the build cache now. We wouldn't be able to do this approach of just build everything on every change if we didn't have that. We would just be waiting days for every change, which is not going to work. It's not enough to just make it fast once. You have to keep it fast. Optimization and a clean house is a continuous investment, and a very worthwhile investment. We know that it makes us faster and more effective, gets our product to market faster. And being faster at fixing, having all that information, as Etienne pointed out, all those techniques, and we just resolve issues better and have this kind of less guessing about what's going on. Yeah, so with that, we'll have a look at any questions that have been posted in during. So the first question that we had is, how do you manage the build distribution when you have dependencies? I'll have to guess here, well, my interpretation of this question is, if you have many small repositories and you're not using a mono repo, how does that work? You will still either need a way to express that many builds and the configuration between them. But the principle of using the build cache to be able to reuse the artifacts that were previously built still applies. You'll still be saving all of that build time. It's just that the interface of sharing things is slightly different. So in terms of the performance aspect, the difference between mono repo and multiple repo isn't particularly significant. The reason why we choose monorepository is that we really value the early integration. So there's no latency between changes in one component affecting the other. I know if somebody just checked in a change to an upstream component 10 seconds ago when I built, it's right there. So it's just reducing the latency for us. And because we can also do it fast with the build cache, that's why we chose that approach. I would say that in a multi-repository situation, I would be even more reliant on build scans because I'm probably going to be less familiar with all of those different projects. So therefore, when I am looking at issues, I'm going to want to be able to find out more about those. But the general answer is it's largely the same. It doesn't fundamentally change the dynamic of monorepo or multiple repositories.
We have another question here. Can you give an example for seed build and downstream build? What is the difference between those? So I mean, I tried to give an example during my demo. So like we run all the compile tasks in the seed build, and then the downstream builds that also need to compile those same components to then, for example, test against them. They can just reuse what has been put into the cache. So really the purpose of the seed build, because that was the question, what is the difference? The seed build purpose is to push stuff in the cache, while the downstream build are then the consumer of what has been put in the cache.
Yeah, so the seed build isn't strictly necessary. We could just make it completely flat and just build everything. The reason why we use the seed build is it can shave a minute and a half off those downstream builds, just in case they run at the same time.
Exactly.
And the compilation hasn't already happened, so you've got two things running at the same time. So by doing a lot of the common work up front, and in our case, we've optimized that particular build and we do it in parallel on a single machine. It's about 3.5 minutes. And because we reuse that so much downstream, that's worthwhile for us to do. So it's a not quite a micro optimization, a bit more significant than that, but it's not a requirement if you want to get started with the build cache.
So is the question related to that, what typically goes into a group when splitting them up for parallelization?
Yeah, sure. So we have two basic strategies here, depending on the type of test suite. So if it's a test suite where it's cross-version testing, so we're testing a bunch of different Gradle versions or plugin versions, we will curate some groups. So we have essentially a group that is the latest Gradle versions, because they're the ones most likely to kind of break for us. And then the older versions we will break up into other groups, just based on size. So there it's a kind of a mix between hand curation, and then we have some code in our build which just says, okay, well, we have 30 old Gradle versions. We want to have 5 buckets, break them up and give them these task names. For the cases, things like our browser tests, which aren't really cross-version tests, we just have a lot of them and they're slow. We just have a small amount of Gradle code that says, okay, look at the test files. Same thing, we want to have 6 buckets, distribute those, create a task for each bucket. And if one of the things we're noting some of the buckets are getting a bit big now, a particular type of test, we're now seeing times of 15 minutes or so, which is too much for us. We need to make that a bit smaller. We'll go in and just change the number of buckets. I think now we have 6, probably jumped up to 15. In the one commit, changed it. Okay, we now have 15 buckets. Change the CI number as well in the same commit. So and that just next time it's like that. So yeah, so we split it on factors like that, and also just arbitrarily just break them up into buckets. Yeah.
And there's a nice side effect that we discussed also with flaky tests. So if you split up your tests into multiple builds and you run them and one build fails because of a flaky test, what you do, you rerun the build, or in our case we rerun all the builds. But because nothing has changed, those that were successful, they will just reuse the artifacts that were put into the cache already. So rerunning the whole chain will only then re-trigger the one build that actually had that failing test in it, which is just a subset of the whole suite of tests.
Yeah, so we have quite a lot of browser tests, and browser tests are difficult to stabilize. We're constantly working on it, but it's a problem we're constantly battling. Yeah. How is the build cache different than using Nexus or Artifactory with snapshots? Yeah, it's a good question. So there's a couple of key differences. One, if you're using something like a binary repository manager, like Artifactory or Nexus, you can configure things in such a way using multiple builds and sequencing builds so that you're reusing things from upstream, but you can really only reuse certain things. Right? So you can reuse the jars as they pass down. It doesn't help you with avoiding tests or avoiding anything else that doesn't sort of propagate via that mechanism. So while it's similar, it's a more, for the case of build performance optimization, it's a much more restricted version, and it only allows you to avoid a particular type of thing. It also requires modeling some of the dependency information that you already have in your build, going what depends on what, out to another tool as well, whether that's your CI tool in order to sequence your builds or something else. At a high level, the build cache is kind of a more comprehensive performance strategy in that any Gradle task that produces files that does work can potentially be avoided and reused downstream.
I think test tasks are a good example too.
Yeah, really good.
If CI runs the test, they might take 50 minutes. Like you say, I run it again locally, but I have no changes. Well, I don't need to rerun the test.
Yeah. And modern builds are about a lot more than just compile and push jars around. There's source code generation, there's UI assets to build, all of that stuff. And it's simple with the build cache. It's just Gradle doing its thing, and then there's this thing making it fast on the side almost. It doesn't require a lot of extra machinery.
And so maybe also to add here is the whole replication aspect that we have at Gradle Enterprise. So we don't have a single cache node. You can have any number of cache nodes. You have the replication. You have the preemptive replication. It just allows you to leverage the performance benefits even more.
Absolutely. So the next question we have is, how can I make the most out of the build cache on a big Android project? Good question, and a very hot question. A couple of things here. I'm not a particular expert on this category, but I can share what I do know. So we've been working very hard with Google for a while now on improving the cacheability of their Android tooling. They're working very hard, we're working hard as well. With the current versions that are available, and you're using the build cache and the Android tooling, definitely check out the build cache fix plugin that we provide that patches some of the issues in the Android plugin that make it more cacheable. And of course, those fixes are being inlined into the Android plugin. I can't remember the version numbers, but I think it's the version that's coming out now that is currently in beta or RC has those fixes inlined. So the situation is improving significantly with cacheability of Android builds. I would say keep an eye on those developments. Apart from that, get started with build scans. Right, so one thing we didn't mention is that while build scans are available in Gradle Enterprise, we also have a free service, scans.gradle.com, where you can go and create build scans for free. A lot of the features for looking at your performance profile and seeing which tasks were cacheable, which weren't, and why are available in that. So create a build scan, share it with the Android community. If you want to share it with us on the Gradle forums, discuss.gradle.org, point it out, we can help you further from there. So at a high level, that's the best advice I can give. So another question here is that we have many small repositories instead of one large one. So this is the multi-repo versus mono-repo situation. I kind of touched on this in an earlier question, but the general answer, can you benefit from these tools and these approaches in that same situation? And the answer is yes. Some things are different, but largely the same issues of wanting to build everything on every change, or at least verify everything on every change, and do that fast are fundamentally the same. Just having the build split over different repositories is not really, as like those things are integrating, it's largely the same. And as I said, we use mono-repo because it's fast enough for us. We've been able to optimize it so that it's fast, and we get that immediate feedback on changes. That's why we take that approach.
There's a question on, do downstream builds trigger publishing to binary repository, or is there no publishing whatsoever? So we still have some publishing, like the build scan plugin that we build, but the publishing is not motivated anymore for other builds to consume it. We also have some Docker images that we publish, But like I said, it's not motivated by publishing so others can consume it, but just because there's external parties of some form that will consume those published artifacts.
Yeah. And because those things are only being published to then be actually used by whatever they're going to be used by, the plugin be used by Gradle builds or the development environments or not, that publishing happens right at the end of our pipeline.
Yeah.
We don't publish at the start before we've done all the verification. So we only publish when we're ready to share with the world, right, when it's passed all the tests effectively. So the next question is, does the build caches configurations of the task or the actual execution? Good question. It's the execution. So what it caches is the work that the task does. So the compiled classes, the source code that was generated, if it's something that generates code from WSDL or something, the test results if it's running tests, so it's effectively caching the result of running the tests. Yes, so that's what it is. So which is the expensive work of a build, right? That's what the build does.
So no question, does Gradle build scans, there's a plugin for Jenkins? Yes, there is one. There was some contributions from a person working actually at Gradle, so use it works well. Then does TeamCity also shows the same information about failed tests? I cannot give a conclusive answer. It definitely shows some information as well, but you definitely have more structure when you look at it in build scans. You have the searching capabilities, you have the per test log. So definitely added value. You have the metrics around how many tests, how long did they take, and so on. And there's more we want to do also in terms of aggregate analysis across tests.
So the next question is, okay, so do you publish the final artifacts to some binary repository like Nexus, or is Gradle cache all the way? Yeah, I think we addressed that in the previous question. So yes, we do, but right at the end of the build, not for performance optimizations or reuse during.
So for those that heard a lot about build scans now, but have never used it, if you just want to give it a first spin, go to the Gradle command line, whether it's an Android project or Java, doesn't matter. Run your Gradle command, build command, whatever it is, add -- scan, and it's going to publish a first build scans to scans.gradle.com, and you will see exactly the information that we showed in scans here. We're not hiding any information from non-enterprise versions. So I think that's a great way to get started.
Yep.
Take it from there.
All right. Well, that's all the questions we received. So thank you for watching. If you want to learn more about Gradle Enterprise, you can go to gradle.com. There's more information about build scans, build cache, how all that works there. The next webcast that Gradle will be doing is about maximizing developer productivity with Gradle Enterprise, which is really a training session. So a lot of the things that we really touched on in scans today and kind of a breeze past will be going much more in depth and really getting into the nitty gritty of how all that works.
Yes.
So if you found this interesting today, it's definitely a webinar. You'll probably get something out of it, how to really get even more out of scans.
Yeah, I think very very recommendable. It's very use case oriented, so people really can see how they can actually benefit in their everyday lives from build scans and Gradle Enterprise in general.
Yeah. So thank you again.
Thank you very much.